It's a pleasure being here today, and thank you for the invitation, Kim. I appreciate that. And let's click the button and we get started. The question is, we know silicon is great, we know germanium is great. What other materials are coming down the pipeline, and is there an opportunity for us to work together and see whether some of these new materials can play a role in silicon photonics or in photonics manufacturing? My lab basically focuses on attojoule optoelectronics. We're really trying to push down the energy per bit to the attojoule regime. We use these devices in optical information processing, in particular in analog compute engines, and I'll give you an example today. And then we also integrate some of those on like flexible substrates for basic IoT devices and systems. So this is basically our group. We demonstrated various devices and structures as basically our Preside already mentioned here, some sort of like plasmon lasers, tunnel sources, tunable sources, index, unity high index tuning, which is quite interesting. With IBM together, we looked into how can metals help maybe bring down the temperature dissipation on lasers on chip, soliton switching, more exotic stuff, and then some more novel material integration on ring resonators, and then we basically use these devices and systems and try to put them into like novel computer engines on chip. And this is work done. I will talk about this briefly. So this is basically like the topic for today. So how can we basically design systems and devices that really are extremely efficient in terms of power? And of course, we know all the applications. So the idea basically is that we use some of these novel materials, which I will share with you today, and then we package them very synergistically with silicon photonics and plasmonics, basically nanophotonic structures on the chip. So that's sort of like our slogan here. The design space is like this. So you have a physical new effect that you're trying to harness, and you have a certain active material which gives you the functionality. This could be gain, this could be switching, this could be modulation or detection. You have an optical mode you need to take care of. There are electrical constraints, and possibly you want to consider a cavity. And everything of this has to be integrated basically with all the optical and electrical constraints that you have on a chip. Why do we scale in transistors? Why do we scale? Well, it turns out we scale fundamentally because capacitance goes down, VDD goes down as we have been walking down 5 volt, 3 volt, 2 volt over the time. If these two goes down, energy per bit electrically goes down quite significantly. Also, once we make our channel length shorter, our ion current goes up. That means our delay goes down. That's basically goes down, which is great. I can put more on the chip, which means my MAC my cost per MAC basically goes down, which is great. So, and of course, we figured out all the scaling laws. So that's why we did it in field effect transistors. Question: do we win if we go in nanophotonics? So is smaller equal better, actually, in photonics for our community? That's something we asked ourselves recently, and the answer is it actually depends, as always. The challenge fundamentally is light is big, let's say 1,000 nanometer at visible or near infrared. Electron, the wavelength is an order of a nanometer. That's 3 orders of magnitude difference, meaning they do not interact strongly. That means my device is hundreds of micrometers typically long, and this is inefficient fundamentally, also energy-wise inefficient. So people look into plasmonics, for instance, or metal optics. So here's my 1,000 nanometer, here's my 1 nanometer. We try to match these two wavelengths. The whole field of metamaterials lives in this space. They say, I take my dipole moment and I make it big. I'm trying to match this. The whole world of plasmonics says, no. I take this big light and I squeeze it down. It's just basically two approaches to the same idea, the same thing, to address the same problem or challenge. There are two other options we can do this. We all know this: cavities. We can increase Q, or I can squeeze my field down and reduce my mode volume. Both basically applicable solutions to this interaction. And this was a nice paper at FIO, just like a conference paper, where the gentleman took like a ring and scaled it down, and you see, of course, Q goes up. So as the mode volume scales down, of course, Q goes down as well. Something we kind of know for a long time. So these are the trade-off. I mean, of course, we know physically what's going on. There's a radiative bending laws, essentially, that how I basically lose my light. That's something we call in the physics world a Purcell factor. So this Q over V is a magical ratio. If I increase this, I win. But let's look at this a little more carefully. So we essentially look at this from 3 different cavities. So this is a ring cavity, this is a Fabry-Perot linear, and this is a plasmonic particle. And we asked, how do they scale? If I make them small, This is the critical length, the radius, the linear length, and here basically my nanoplasmonic particle. Do I win? And the answer is I win to a certain extent. This is basically our performance. This is Purcell factor. Up is good. So you see these are color-coded here naturally. So you see basically there's a certain peak that I can achieve, which is reasonably high actually, for a ring resonator. So ring actually is pretty good because it scales fairly flat with ring radius, but at some point I'm getting bending radius, and basically I'm losing Q. But at the same time, as I'm scaling down, my radius, basically my mode volume walks down linearly in this log-log plot, linearly. So naturally I have a peak. And that peak is pretty interesting, actually. This would give me quantum mechanically actually like strong coupling almost, because it's 10 to the 3. But that's maybe for another topic. The Fabry-Perot is decent, but overall Q is lower. Also, as I'm scaling, as I'm squeezing these two metal mirrors, I'm forming actually eventually like a metal inside a metal mode, so my mode direction switches and I don't have any more confinement. That's why basically the Purcell drops very drastically at some point. The plasmonic part is interesting. Now look, I can actually go to like tens of nanometer small cavities and yet have a reasonably good Purcell factor. But eventually I'm still losing as well. So we cannot go to extremely small, although this is already like tens of nanometers, already reasonably small. If you normalize this interesting fact, this Purcell factor by area, interestingly, plasmonics looks interesting. And then we look into devices. Basically, we look into how a laser, modulator, and detector performs. And we benchmark them against basically the energy per bit, and there's an electrical part and an optical part. The optical part is basically, let's say, for example, in modulator, we have something called power penalty. This is basically your, so the optical power penalty is basically like your on-off switching, your on state. Then it's basically the average power the photodetector sees downstream. And then, of course, the eye closure penalty, which is something related to the classical DC extinction ratio. So we need to take care of both, electrical and optical energy. The second one is speed. Again, electrically and optically. What's the optical speed? So this one, like we all know. What's this one? This is basically like the photon lifetime. If I have a high Q, my photon stays long time in my cavity, and I cannot remodulate my signal. So of course, I have this basically this averaging effect essentially. So what's the figure of merit? Well, it's basically my data capacity over the power times the cost. So what does it mean? It basically, let's say for modulator, it would be my 3dB bandwidth over energy per bit times the area, for instance. So naturally, if I can make my device small, but I'm losing my effect. So there is a fundamental trade-off. But if I go small, I can make my capacitance small, which is great, and my energy goes down too. But again, the effect versus the performance is a fundamental trade-off. So I need to balance these two. Just two slides for example here. So one is like the laser. So this is the laser threshold. This is like the rate equation. You can solve this, and you get this long beast here. And essentially, there are like three terms that are highlighted here. And essentially, we see at the end of the game, if I increase this Purcell factor, actually, I do win. This one actually hurts me. This cavity loss hurts me. My threshold increases. The gain absorption rate decreases, so my threshold actually decreases. This is good. And the pump efficiency, basically, I'm getting more photons into the mode that I want. But this basically means my spontaneous emission beta factor is very high, which is, again, related like raised to Purcell factor. And long and behold, actually, it's matches. See, for all cavities, the lowest threshold, so here minimum is good, is where I have the highest Purcell factor. So the threshold scales inversely proportional with Purcell factor. And again, I can have a reasonably good Purcell factor in plasmonic systems, which are now orders of magnitude smaller than in my photonic systems. That's sort of like the question mark. On the other hand, my threshold is actually higher than in plasmonic systems than in photonics. Can I tolerate this? The answer might be no, something we should discuss probably. For electro-optic modulators, so I have light in, I basically switch it, I have my light coming out, so I have an electrical, like a field effect here, and a capacitance. So my energy, my electrical is 1/2 CV squared, so I take my C, I plug it in here, that's my capacitance. Here, voltage is E times H, I plug it in here, squared. Now 1H cancels, and then I basically pull out all these geometries, and guess what? This is just simply my volume. Okay, that's interesting. And then basically here we have a relation for the electric field, which depends on the bandwidth, and then this depends on Q. I can plug this in here. And essentially, if you look at this, it's volume over Q. That's again 1 over Purcell fact. But there's one more Q in there. So laser scales 1 over FP. The EOM scales 1 over FP times Q, so Q is more important. The detector, actually, there's some interesting relationship still with the scaling, but Purcell factor, we're not 100% clear. I think we should discuss this. And then we also look at all optical switching devices, which depends also 1 over f actually q squared if you're in a second order effect, and simply linearly if you're in third order. So third order helps a little bit, actually. Leutel's group looked into modulators and also said, if you want to have a very high switching, that means if you have this high, you can make the device small. Your overlap factor needs to be very high. Your material switch needs to be high, and you can have a slow light effect, meaning your interaction is basically enhanced. And he basically compared us, for instance, here for already like a silicon slot, which is already confined, but then to a metal one, which is even more confined. And essentially, we see as he essentially goes from the photonic to the plasmonic one, his overlap factor increases, his slow light effect increases, and his overall switching is pretty strong, actually. So now Kim asked me to basically talk a bit here about these new materials. So I call this my active material, which is basically, that gives me this basically my action. And here's an example for modulation. Of course, we have apply voltage, change the effective index. We have an Pockel's effect curve, Franz-Keldysh, quantum confined version, electric carriers. And there's a whole bunch of, there's a whole fleet of options you can choose from. We all know them. So there's carrier-based ones, silicon, 3,5, graphene, transparent conductive oxides, phase change, thermal effect. And they have also some sort of pros and cons, but Kramer's chroniculation in physics fundamentally tells us that if you change your real part, you change your imaginary part. So you want to get some sort of phase change, you always take a hit and loss. And the question is there some sort of win-win that you can actually possibly achieve? And the answer is actually, it turns out a cavity can help, and the answer is yes. This is ITO, so this is simply the Drude model. Essentially, what it means here, this is like a real part. It shows as a function of carrier concentration, you can very drastically change this index. And here, basically, here's the real part, here's the imaginary part. You can really see, you can change it by unity, essentially. It's quite interesting. You can also change the loss very dramatically. And this error here, incidentally, is a device we made in the past in this paper here. You also notice if you get to this point here where this tip ends, you actually have E and Z, epsilon near 0. So your wave is flat. And then you have a very strong interaction with your system. It's kind of an interesting point to play around. ITO is an interesting material. Depending how you process it, you get all sorts of different results. This is literally all ITO, and you see physically it looks very different. It has to do with like resistive well. Too much oxygen gives you high resistance. Too much tin gives you resistance. So there's some sort of resistive well structure. So we did ellipsometry. We characterized this, and we basically found you can actually get basically 0.15 actual K switching in your material and basic unity index switching in the real part. That's transparent conductive oxide, so it's good for switching. How about 2D materials? You heard about them. So graphene, semi-metal, yeah, some other materials which have a wide variety of band gaps. They're also insulators. And they're also interesting materials for active photonics. This is, for instance, graphene here. Graphene has something called like a Pauli blocking. So essentially, if you look at the conductivity is something like the permittivity, like your index. You can basically change that. You get for a single sheet of graphene, you get basically about 2% of absorption, and in the near infrared. But it turns out we can actually change this. I think my battery just died. And we can actually tune this significantly as well, like over this range. 2D materials are interesting, and this is sort of like the case here I want to bring today. So if we want to go to like small compact devices, form factor actually helps, so it's very synergistic. It has a decent okay mode overlap. We get a strong switching. It's electro-optical tunable. We can control the composition, and we can pattern it in your foundry. We can put it in CVD, and we can basically pattern it to the areas that we like. And it's compatible with the substrate. So unlike 3.5, essentially 2D materials at a quantum well you can put essentially anywhere. And you essentially preserve the quantum well behavior of this material. So they come in various flavors. It's like one metal and two chalcogenides. And it's like a buffet style. You can sort of pick and choose and then get various properties. If you look at this one here, there are a whole bunch of band gaps that are available essentially. You see theory and experiments still have to do a bit of work essentially. What's interesting is if you have a bulk and you go to 4 of these layers, 2 or 1, as you go to a mono layer, they become actually direct band gap. So They have a very nice properties, and as they become a direct bandgap, basically we see their their photoluminescence is increasing, and people have recently shown that you can have essentially 90+% internal quantum efficiency. So for lasing, that would be interesting, and for photoconduction. We can tune them, for instance, from like molybdenum sulfide to selenide. We can alloy them and tune them. We can make junctions. This may be interesting for solar cell, where you do spectral splitting and optimize each cell for your wavelength. And this one slide about physics, essentially what's interesting is they have something called a high oscillator strength, which basically means you can, again, have a very strong electro-optic modulation. Here, for instance, is basically shown like a very, if you have one layer, it's basically all the way up here. For multi-layer, it's basically all the way down here. So, and there's a like break here in this slide. So for modulation, the telecom band, you would essentially expect a very strong switching, and we are doing this right now. We're using these materials and interfacing them with like Silicon-Photonics or Silicon-Plasmonics. You need to watch the modal overlap factor. So if you simply use silicon, silicon has in refractive, like a plasma effect, you can tune your mode, but in order to get a decent switching, so up is good in this plot, you need to have a very strong, basically overlap factor, which means you need to make sure the entire mode basically is changed. Even if we do this, we only get like medium amount of switching, basically like on this level right here. It turns out if we, for instance, use graphene, or use this graphene effect, or this ITO effect I told you before, essentially we can actually get away with much lower overlap factors and get a significantly higher switching already. And these are some actual devices here. This is like a graphene device, and this is like an optimized device we recently looked at. You can look at a whole bunch of modes. So this is basically like all like bulk modes. These are like slot modes and hybrid modes. And look, well, is silicon actually a good choice for an active material? Or maybe should I use these TCOs or maybe these graphene materials? And we mapped out all of them. And here is how the mode look like. So you see some of them give you like very strong confinement. But what's really interesting is once you interface them with a cavity, something interesting happens. So first of all, so again, this is as a function of cavity scaling length here. So the question is, do I win if I make my cavity long? And if you have a bulk mode, a classical bulk mode, the answer is yes. So red color means it's good. So if you have a bulk mode, you make a cavity long all the way to the right here on each of these type of plots here, basically you win. We also see ITO and graphene give stronger switching than silicon, so the color is darker. That's interesting. If we go to sort of like nanoscale systems, what we actually see here is that high spot is not for very like large cavities. It makes sense because the mode is fundamentally lossy. It has some metal in there. That means if you go too small, like you don't get any switching. If you go too long, you have too much loss. So naturally, we are expecting some sort of optimum somewhere in between. And if you look actually where it is, it's not bad. It's around 1 micron. So it means I can make my device, my entire switching, let's say modulator, now a micron, and I'm okay. Moreover, it turns out if you work on this ENZ regime, you see these colors slant to the left here. This point here, this is basically like the carrier concentration for this ENZ regime. And that essential regime, if you follow the sort of like orange color here, from here to this point, it slants over to the left. You essentially, like, we win by a factor of 10. Now we can make 100 nanometer long devices, which preserve the same functionality as we have typically in tens of hundreds of like devices. So this is an interesting direction we are basically looking at. So let me give you just a few examples here. This is a module that we made in the past on this ITO. It's an MOS type structure where in this, it's like a MOS capacitor literally, and we put in this hotspot here. This is our optical mode. It's a hybrid plasmon mode. In that hotspot, basically, we put our active material, and then if we switch it, basically we see this is a transfer curve here. This is like your transistor IV curve essentially. This is your light versus voltage. For a 5 micron long device, we get 5 dB of switching. For 20 micron long, we get 20 dB. This is 1 dB per micron. And if we leave out the ITO, nothing happens. So we know it's the actual effect. This is how the device looks like. This is Silicon-Photonics and hybridized with this like metal plasmonics and ITO. And again, the whole structure essentially is simply like 3 lambda long. That's all basically that it needs. The performance, again, we can scale it down. So I call it scalable speed and power. So we can make the device now in the order of like a micron or less. The RC delay and also the internal switching time is fast. We are still working on demonstrating this at this speeds, but we are making good progress. And again, the power is on the energy per bit. Graphene is interesting. You can this is the actual refractive index now, and you can bias it as shown like here. where essentially the real part changes dramatically, but the K doesn't change much. And this essentially would allow us to do like a phase change device. If I simply bias it over and shift it to here, to this regime, my real part doesn't change much, but my K changes, and I can basically make a linear like electro-absorption type of device. With this, we actually demonstrated the first plasmon electro-absorption modulator recently. This is how the device looks like. Again, we use this confined mode. And if you look at the switching basically here, so this is like your optical response as a function of voltage. You see it's less than 1 volt, so it's basically 0.7 volt. And the reason why this works so well, unlike some previous works which used 4, 5, 6 volts to switch, is we have a very good electrostatics. And this is basically enabled because in this device we can have this metal, which is our plasmonic mode, so it's basically a plasmonic mode confiner. It is an electrical contact for free. And this means we have fundamentally a very low resistivity. And resistivity basically comes in this equation here in this A0, which is basically like a resistive term, and into this into this voltage term. Which means if you think about it, any photonic crystal cavity that you have, for instance, or any photonic structure, and you bring a metal close to tune it, to modulate it, to do something electrically with it, you hurt the mode, you destroy the mode. Which means that's a fundamental problem, for instance, like in photonic crystals. You cannot really tune them well. With these plasmonic hybrid systems, you get this contact for free. And this means now your electrostatics is strong, your resistance is low, which means your overall performance is high. And this allowed us to basically have the first sub-volt basically switch. Also, you have, of course, heat dissipation. All right, so here's a performance chart to kind of sum it all up. In ring resonators right now, we have a figure of merit. This is the speed over the energy power penalty times the area in gigabits per femtojoule per micrometer of that value. If you go to simply change the active material in SOI to graphene, still SOI, photonic mode, we already win by 3 orders of magnitude. We can go to plasmonic structures. We go to 10 to minus 2, so it's significantly better, already in order of magnitude. Or if we hybridize it now in this fashion, as we've shown here, we again win like basically on the footprint, and we can again probably from here to here win another by maybe 2, possibly 3 orders of magnitude in terms of scaling. What can we do with this? So photonics, we know it's great, it's diffraction, but it's diffraction limited, so it's somewhat large possibly. So the footprints of devices are large because the interaction is low, the light interaction is low, the energy is possibly on the higher side, but they propagate long, which is nice, I can use them on a chip. Plasmonics, on the other hand, is not limited by any of these. It's more efficient, possibly, but of course it doesn't propagate long. So the question is, can we simply take the best of both worlds and hybridize the two and get good switching, good scaling, and high bit flow densities, etc. And we published this in this recent paper where we've asked fundamentally, if I have a link now, can I make like a plasmonic hybrid link? And how does this compare to electronics or photonics or pure plasmonics? And here's basically the result. So if you have electronics, you're limited by your capacitance fundamentally. In plasmonics, you need repeaters every 100 micrometer. That's basically unfeasible. Pure photonics is decent. Actually, that's our Silicon-Photonics. And if you hybridize this, hybridizing means the active device, the source, the modulator, and the detector is basically a plasmonic device, and its interface with Silicon-Photonics, we end up in this regime right down here. And the third axis basically is our bit flow density, so how many bits per area. So this brings me to a power roadmap. So you probably want to all go know where are we going with this. And this is basically where we see the big picture. So right now, this is classical. This is what I call my Silicon-Photonics. So right now, we use hundreds of femtojoule, maybe down to 10. In fact, a few femtojoule. We heard the talk earlier. So we're really pushing this down to this like 1 femtojoule limit. But we pretty much, if I tape out something in the foundry, I'm pretty much sitting basically up here. That means fundamentally, 100 femtojoule means I'm using 10 to the 5 photons per bit. So that's when I talk to used to talk to Mari Panicia, and he asked me, you have a laser? And then he asked me, how much power do you have? And I said, well, nanowatt, he was not interested. He wanted milliwatt. Well, that's basically why. Because if I multiply now the energy efficiency times the bandwidth, essentially, so that's basically joule per bit times bit per second. That's joule per second. That's watt. That's the third axis is simply power burned. And yeah, that means right now on a single device level, we use milliwatt. The question is, can we bring this down to maybe microwatt? And the answer is probably yes. If we go to this like nanoscale regime, which means you see these ISO power lines here, this arrow is steeper than the ISO power lines. And again, bandwidth is the other factor. If I have this large device, which I need a long interaction length, I need millimeter or maybe hundreds of micrometer long interaction length. That means my RC delay is high. that means my bandwidth is fundamentally high as well. So the idea is if we go to this nanoscale regime, essentially I can go to like micron scale devices and my bandwidth maybe approaches 100 gigabits per second or maybe even beyond. Of course, you see quantum down here. I think we're not there yet probably because then we run into SNR issues and a bit error rate issues and so on. But that's basically like our direction. There is nothing is free, right, in life. So there's a Q over V. This is basically like the amount of per cell factor you need to introduce into your system to make this happen. But these values are reachable right now experimentally. So that's basically like the big picture here. So now we have links. Now you can go to compute systems. Energy efficiency on the y-axis and x-axis basically is sort of like your speed, well, normalized per area and per second. So in electronics, we know electronics is great, but electronics is fundamentally limited in terms of speed, but also in terms of like actually like power dissipation, which is heating up these wires, their ohmic resistance, that's basically lossy. If we go to something that's like sort of photonics, essentially like we use the bosonic character of photons or of RF waves in a way, you have more parallelism built in because photons, like bosons don't interact strong with each other. So that's basically good. So we can basically like increase the speed, but they don't scale well. So the question is actually, can we go beyond this? And this is basically a direction where we're trying to map directly the computation that we want to get done. We don't want to do like ons and offs anymore. We want to directly have some sort of computation done, and I map my algorithm to my hardware directly one-to-one. That means I sort of use the hardware itself to basically do my like not give me zeros and ones, but give me directly maybe in differentiation, or give me integration, or give me an FFT directly, just like by propagating through my structure. And photonics is basically very good at this. So we are basically working on this one, this scheme. And here's one example I brought to you before I wrap up. This is an optical arithmetic compute engine. The way it works, basically, we recently designed this. This is basically like a 2x2 switch. And it's a hybrid photon silicon-photonic plasmonic version. It's just like 5 micron long, and it uses like less than 1 femtojoule per bit. And we have a patent on this with Richard. And we basically now package this into an optical router. And this optical router now is basically doing optical arithmetic. So it's basically like a modular scheme. So imagine you want to have the number 17, and you have a basis of 4. So you do like 17 divided by 4, it's 16, 4, rest 1. So what you do, you have 4 waveguides coming from top, 4 from the bottom. What you simply do, you basically route 3 of them, 1 over, and this one that was on the left all the way over here. So that would be like basically like residue 1 or modulus 1. And it's a multi-purpose compute engine. And the way why I think this is interesting again, because a photon, we all like photons. Photon has momentum, and momentum, so mass times velocity. So if you can never essentially slow or stop a photon. If the velocity would go to 0, the mass would go to infinity. That means fundamentally, a photon must always flow. You can never stop unless you kill it, unless you annihilate it, right? You detect it. So the photon must always flow. Can we, while we flow the photon, get computation done? And the answer is yes. With this algorithm, basically, we can. And you can think about it as it's an in-the-network compute engine. And if you look at the numbers down here, probably too small. Actually, it's very competitive. In fact, it's about 3 orders of magnitude better than basically current NOC with 22 nanometer technology node. So this feeds this one. And then my last slide here, this is a slide I made about 1.5 years ago when I was excited about IMES. So one of these devices is a photonic device. The other one is an electronic device. Would you know which one is which? Any guesses? Well, that's the whole point. The question is, so it turns out the left one is actually a transistor, is in FinFET, and the right one actually is, from Miller's group from Stanford, is actually a plasmonic enhanced antenna device. The point is, CMOS is really, so the question is, are we as photonics people driven by CMOS, or are we driving now CMOS? I think the chicken and egg thing is maybe possibly switching now, right now. So I think this is something that got me excited at the time. And what's great about this is, yeah, we can design these 100 nanometer small metallic structures like routinely in CMOS. So, and again, with these devices, we will probably harness this right now. So I think this is some interesting discussion we might have over lunch. So these are just some conclusions here. Let me just point out this one essentially again. The main point is I believe due to chronic relations and due to these strong switching effects in these new materials, we actually have a true opportunity right now to address the optical constraints and the electrical constraints simultaneously. And we can discuss maybe what that might mean. So these are all my collaborators. Thank you very much.
So there was a lot in that talk, so perhaps somebody has a quick question before we leave for lunch. If not, I recommend Kim does.
Quick question. A question about two aspects of what you said. One is, do we have a scaling vector for photonics? For photonic shrink. And then secondly, you mentioned we can get contacts for free with a hybrid structure. Can we use those to eliminate the contact loss in the more classical photonics?
Right. The contact loss, I believe, we can use them at least electrostatically. I've not investigated personally whether we can use them to maybe actively inject carriers. It's something we looked at with IBM. So we actually published a paper on this, and it suggested that it might work, but it was just simulation at this time. It was not. We didn't demonstrate the actual device. So I think for electrostatically, I definitely give it a yes. I know it works. We made some devices, but for injecting, that's maybe still yet to be seen. Do we have a scaling vector for photonics? I believe we do. At least since we did this sort of scaling analysis now. In fact, it was really like Thomas said in the audience. It was really like motivated by Thomas' work from your 2011 paper, from your conference paper, where he looked into some sort of scaling for basically for modulators. So we said, this is interesting. Can we look beyond this? And it sounds actually that we have some scaling vector. At least I would say down to maybe the hundreds of nanometers right now. So I think an order of magnitude looks promising. Then things become really probably we need to then discuss about the bit error rates and those kind of questions. Thank you.
So let's thank all of our speakers again, please.